Friends, now we'll see the part C of the question number 5. The experiment is repeated with the spring of spring constant 4K naught and has the same length as the original spring. The same object of 0.5 kilogram is hung from the new spring and allowed to a rest in a new equilibrium position. The question now asks, determine the new equilibrium position above the motion detector. Initially, this was the situation. So the original, the length of the spring is the same. When nothing was hung from the spring, it was 1 meter above the detector. Okay. When you hung the original spring with spring constant K naught, the object you hung from the spring from this position, it came down a height of 0.4. That means this was 0.4 meter, hence this was 0.6 meter. 0.6 meter was the position of the equilibrium in the case when we had the spring of spring constant K naught. In this situation, with the new spring now, the spring constant is 4K naught. So when you hang the mass in this one, it will still be stressed, elongated by some amount, but not the same amount. We have to find out this position. How far above the detector is the object hanging now? The equation of motion, the equation of force is still the same. Okay, the spring, the force due to spring is balancing the weight mg in both the cases. The equilibrium position is shifting because the spring constant has changed now. So initially, the elongation in the spring was that of 0.4 meters to balance out the weight. That means 0.4 times K naught is the weight of the object. Weight is mg. So we have to find out what is the elongation in length for the new spring. So let's say that is the elongation is something. Let's say x naught. Okay. So 4 times K naught times the new elongation. X naught is the elongation from the natural depth is equal to, still will be balancing the weight, same weight, and we take the ratio. This is mg by mg is 1, and this on this is how much? 0.4 K naught upon 4 K naught x naught. K naught cannot be cancelled. So x naught is coming out to be 0.1 meters. That means the elongation from the natural length, the new spring will be elongated or stretched by an amount of 0.1 meter or 10 centimeters. That means from the detector, it will be at a height of 90 centimeters or 0.9 meters. So this is the position. The new equilibrium position is at 0.9 meters above the detector level. Okay. Now the second part. The object is again pulled down the same distance d naught. After once the object is hanging in the new equilibrium position, it is further pulled down with the help of some external force. It is pulled down by a distance d naught from the equilibrium position and released. On the following graph, we have to draw a curve representing the motion of the object after being released. So we have to make the same graph for the new situation with the new spring here in this case. So basically, since we are pulling it down with the same distance d naught, the amplitude is still going to be the same. The mean position we have just found out 90 centimeter mark. Earlier it was 60 centimeters. The equilibrium level was at 60 centimeters. In this new situation here, it is at 90 centimeters. The amplitude is still going to be 5 centimeters. The height is going to be 345. So let's say this is in centimeters. So this is 95 centimeters and this is 85 centimeters. The amplitude is still going to be of 5 centimeter only because you are pulling it by the same distance d naught. That was the amplitude of how much you pull it down from the V. So that is 5 centimeters. What about the time period in the earlier case? We saw time period in the earlier case when you had a spring of spin constant K naught, it was 1.25 seconds. Okay. 1.25 seconds was the time period. Okay. That means the curve was, it completed one cycle, one period, it was of 1.25 seconds. Now we have to find out how much is the time period in this case. So, time period is given by 2 pi root of m upon k. The time period in the previous case was 1.25 seconds. So T1, I say the time period in the earlier case, it was 2 pi root of mass is still the same upon k naught. The new time period that we have now should be T2, if I call it, is going to be 2 pi square root of mass still the same, but the spin constant is 4 times k. Okay, so 4 k naught I write. If you just compare these two, you see that the 4 is in 12 here, it will come out. So when we compare T1 and T2, you'll find out that T2 is nothing but half of T1. So the time period in the new situation is half of what it was previous. Okay. So that means if the time period we completed one cycle in 1.25 seconds, it will be doing so in half that time. Okay. Right. In 1.25 seconds, it will be completing two cycles. So the half of 1.25 is 0.625 seconds. Okay. So in this one, from 0 to 0.625, it will complete cycle. And it is starting from it is starting when the height is 85. It is being pulled down further by 5. So it is starting from here and will complete cycle. So if I try to make the graph, you will see like that. Okay. So you see, it is completing one cycle in the time interval of 0.26, 0.625 seconds. Same will be repeated after. It is going to repeat. So two cycles will be completed until this point. So you see, the amplitude is still 5 centimeters, but the time period has been halved for the new peak. In a time interval of 0 to 1.25 seconds, it is completing two cycles now. Okay. So that is what time period is. Right? So this is the new graph that we can make. The vertical and the horizontal axis, they have been labeled. This is the height from the detector, and on the x-axis we have the time. So this pretty much answers the question. Okay, thank you.